So I'm Yang Li, and this is a joint work with my colleague Hao Lu at Google, who unfortunately couldn't make here. Because you're going to ask me a question at the very end, so I want to ask you a question now. What is the most common thing you do on mobile devices today? Check time. And what else? You got it. Okay, so the list here probably captures some of your favorite apps. But in fact, one thing we actually do a lot and we often don't realize is actually the process to get to these target functionalities and apps. So typically, a user needs to turn on the screen, unlock the phone, and then navigate a deep URL hierarchy to get to a target, right? So the process here is tedious and time-consuming. So if you think that the effort here is trivial, let's see how often we have to do this. According to this report from KPCB, a major venture capital firm, on average, a mobile user access their smartphones for about 150 times per day. So this is actually a lot. And a log analysis I did indicated about 50 times per day per user. The user has to go through this process. So this additional effort is actually like heavy taxation on mobile access, and that's the problem we want to address here. So we developed this system that allows users to quickly access mobile devices using gesture shortcuts directly from the standby mode. Say we want to start the YouTube app on the phone. Before we even turn on the screen, we can simply draw letter Y on the screen. And the system returns a list of results where we can quickly activate the YouTube app. So this is how fast we can access the mobile device. So this is cool. We can do the mobile access without having to go through all these additional steps. But as you can imagine, to achieve this functionality, we have to address all these problems here. For the rest of the talk, I'm going to talk about our exploration for some of these problems here. So for this to work, we need to continuously sense user input. It's quite possible that the user accidentally touched the touch screen. For example, when the phone sits in the pocket, or when the hand actually touched the bezel of the screen while holding the device. So the first problem for us to address here is to be able to tell intended gesture input actually from accidental touches. So to do that, we instrument a set of Nexus 5 devices to constantly sense user input as reported by the touch screen, the proximity sensor, and the accelerometer, as well as other sensors. We asked a group of participants to use these devices as their primary phone for a few days, and on average, each user generated about 800 accidental touches per day. So these are a lot more than what we would expect. We also asked the same group of people to draw character gestures in a variety of conditions, including using the phone single-handedly versus bimanually while the user is walking or sitting. So these experiments generate a good set of data set for us to better understand how intended gesture is actually different from accidental touches. Next, I'm going to give you a few examples about our analysis. So both intended gesture input and accidental touches generate so a sequence of points which we refer to as a stroke. So the heat maps here show how these touch strokes are actually distributed on the screen. Just to clarify, we use the farthest point on the stroke to the bezel as the location of the stroke. So as we can see here, accidental touches are actually distributed almost uniformly on the screen, but for intended gesture input, they are quite concentrated at the center of the screen. So this is because accidental touches, they occur more randomly, but for intended gesture behaviors, users tend to choose the center area of the screen for articulation. So the randomness of accidental touch is also reflected in the sensed pressure value. As we can see here, for accidental touches, the pressure is basically spread all over the pressure range. But for intended gestures, there's much less variation in terms of sensed pressure value. And the difference of these two types of behaviors is also well captured by other sensors, such as the accelerometer. As we can see here, the acceleration doesn't actually change much for intended gesture input because the user tries to keep the device stable during the articulation, but that's not the case for accidental touches. So as we can see here, each of these features is it's actually good at capturing certain aspects of the difference between these two types of behaviors. So we built a decision tree model based on 8 features. We achieved good accuracy in terms of precision and recall. So next I'm going to show you how the system actually works in detecting intended gesture input and ignoring accidental touches. So these accidental touches will not trigger any actions. But once the user draws a gesture, the system responds right away. Okay. So because now we need to continuously sense user input, battery consumption has become a very important problem. With our current implementation, the battery can only last for a day, right? So because we have to keep the CPU running all the time to do the continuous sensor processing. But several modern smartphones have already adopted the architecture of using a low-power DSP chip to continuously process sensor input. But it's hard for us to actually access these co-processors on existing platforms. So to find out our battery consumption in such an architecture, we used an external approach by experimenting with our gesture detection code on a low-power DSP chip that has been used in Apple iPhone. So the experiment indicated that our battery consumption is negligible. So both the high detection accuracy and the trivial battery consumption indicate that this always-on gesture approach is actually feasible. Okay, so far we have conquered the problem of continuous gesture detection. The next challenge lies in the process of mobile access is user authentication. So as we know, authentication is a very important feature to keep the mobile device secure. So these are some examples of authentication in existing commercial products. So one is to require you to enter the passcode, and the other one is to cross the dots for a specific pattern. Although a lot of design consideration has been put into reducing the effort for authentication, they still require a dedicated effort from the user that has nothing to do with the target action the user wants to perform. So can we actually use the gesture the user draws for retrieving the target and for authenticating the user at the same time? Handwriting-based authentication has been studied formally, especially for signatures. But the problem we need to address here is can we to authenticate the user based on a single character gesture the user draws, which potentially has much less biometric information. Let's try to be more precise about the problem we want to solve here. So given a set of template gestures from the user, we want to find out if the gesture is actually authored by the same person. Because the biometric information changes a lot when the user draws different symbols, so what we do here is we first we're trying to evaluate the gesture given each gesture category, right? So how well the biometric information of the gesture actually matches the template for that gesture category. We then combine the outcomes of these matches with the probability that the user is indeed actually drawing the gesture symbol. So these templates can be provided by the user after the system is deployed, but the entire prediction model here can be trained offline. So that is a good thing because we can collect a lot of data to make the prediction model work really well. So we did the experiment to evaluate the quality of our simple authentication method. Overall, we achieved 25% false negative and positive rates. So this accuracy is certainly not sufficient for actual use. This is partially due to the lack of biometric information in a single character gesture the user draws. But there are several ways to improve this. So one approach is that we can potentially acquire more richer biometric information by looking at more user gestures and also looking at other sensor signals such as motion that has proven useful in prior work. And another direction is we can dynamically adjust the decision boundary to make our authentication mechanism more or less sensitive to the biometric variation for tasks that have different balance for efficiency and security. And lastly, actually, authentication has become less of a problem as wearable devices actually become popular because so when a smartphone is paired with a smartwatch, the phone can be automatically unlocked. So once the gesture is detected, we need to infer the target the user wants to access. For example, we need to infer YouTube from the single character gesture letter Y. So this part of functionality has been addressed previously by several shortcut systems. So in our current implementation, we connected our system with gesture search. It's publicly available, and it allows the user to quickly access a range of targets using gesture shortcuts. But as you can imagine, we can easily connect this system with other gesture shortcut systems. So in conclusion, I have presented a system that allows the user to quickly access mobile device using gesture shortcuts directly from the standby mode, and our methods for achieving this functionality. With the system, we hope a target the user wants to access is always just a couple of gestures away.
ask you any time, but I'll just ask you now. The measure of the battery, did that include the touch sensor power, or that's just the coprocessor power?
That's a good question. So actually, it's measured in a simulated environment, so it doesn't include the battery consumption of the sensors. So
Which
basically,
which could be the more major part. I know they do a lot of tricks in activating and deactivating sensor to conserve battery.
right. So some exploration we did indicate that the major battery consumption is actually on the CPU power. So sensors actually, I think on these modern platforms, they are optimized quite a bit. So battery consumption there is not, I mean, it doesn't seem to be a big problem. So the major battery drain is for the CPU processing. Seems to be a problem.
So the coprocessor removed that part as the bottleneck.
Right.
But the sensor itself, by then, would be whether that's still a bottleneck is unknown, or you say that's just not a sensor's not.
Yeah, actually, this is probably a little bit more detailed about the implementation of the system. So actually, touch sensor somehow is on most of the time. So even when the screen is off, actually touch sensor is on. But it's not on all the time. Then we had to periodically check if the touch sensor is on. But the fact that the touch sensor is on even after screen is off, it tells us actually it might not be a big problem for battery consumption.
Yeah, I guess depending on the device, they also have different modes, and some modes are more battery consuming than others. The touch sensor itself.